Hello, I'm Lou Bloomfield and this is How Things Work. Today's topic, rockets. Rockets make use of a familiar concept, at least one that shows up in everyday language as action and reaction. For every action there's an equal and opposite reaction. More specifically, to sort of put the physics in that story, it makes use of Newton's third law. Rockets depend on the fact that if you push on an object, that object pushes back on you equally hard in the opposite direction. And ultimately that's what propels rockets forward. Well, to tell the story more completely, let's look at the following thought experiment. Suppose I'm in the middle of empty space, nothing else around. I'm here in front of you with the camera still filming me, and I'm not moving. And for some reason, I want to head to the right as you view me. I want to go that way. There's a fast food restaurant over there that I really want to check out. If I want to go that way, I need something to push me. And since I'm not near any planet or anything like that, I can't go look for things outside of my immediate vicinity to push on me. All I happen to have, though, in my story is a bunch of baseballs. I happen to have a skateboard too, and I could do this story standing on the skateboard, but it would be very brief, and then they'd have to cart me off to the emergency room after I fell. So I'm not going to stand on the skateboard, okay? But I am going to play with the baseballs, at least in thought. Okay, so I've got the baseballs, and I want to have something push me to the right. What's it going to be? Well, I can ask the baseball as politely as I like, but it's not going to push me to the right in a useful manner unless I throw it. If I throw this baseball to the left, watch what happens, or let's think through what happens. In the act of throwing it to the left, making it accelerate towards the left as you view it, I have to push it. It doesn't accelerate for nothing. Forces cause accelerations. So in order to get this baseball moving toward the left, I have to push on it with a force. And as required, as observed by Newton's third law, the baseball will push back equally hard on me. So if I can push on the baseball, and I can't do it for very long, or possibly very hard, in the act of throwing it out, I don't want to do it because it'll bounce off. There's a wall there, it'll bounce off, and this will be, comedy rather than, well, it's comedy anyway. Okay, but if off it goes, as the baseball goes off, carrying away, moving fast, carrying away momentum to the left, I will end up being pushed to the right by the baseball, and I'll leave, off it goes. Now I'll do it a little bit. Off it goes, I'm carrying momentum to the right. The fact that I push the baseball to the left requires that it push me to the right, and that propels me toward the right. And I'm good, I'm heading off to the restaurant. We can look at that actually in two ways, and I mixed them just a moment ago. But one of them is in terms of the forces. If I push it to the left, it pushes me to the right. We can also look at it in terms of momentum. We started, the two of us, me and the ball, we started with zero momentum. How so? Our velocity is zero. So yeah, we've got mass, but no velocity, so we've got no momentum. But when I throw the ball off to the left, it has its small mass, but it has a big velocity. So it's carrying momentum in the direction of its velocity, namely to the left. And I, in turn, will carry an equal amount of momentum to the right. The sum of those two pieces of momentum, the ball's momentum to the left, my momentum to the right, will still be zero. We started with no momentum. We're not interacting with anything else in the world, just us. So we can't change our total momentum, but we can distribute it funny. I can give leftward momentum to the ball and get an equal dose of momentum to the right in myself. And off we go in opposite directions. And that's really the action-reaction associated with rockets. That is how rockets propel themselves. Not by looking to the world around them for pushes. Instead, they look within themselves for parts of the rocket that they can throw out one way and have, as a result, a push in the opposite direction. So rockets consume fuel that they started with. When a rocket launches, it has sort of two pieces to it. It has the craft itself, the spacecraft itself, which is going to all be heading in the direction that the rocket is supposed to go. And it has fuel. And whether it's literally fuel or various other things, it could be the deck chairs inside the rocket. Just the mass, the stuff that will be thrown in the opposite direction. And how it's thrown doesn't matter. It turns out you want to throw it as fast as possible so it carries away as much momentum as possible. And you get the rocket, the craft ends up with momentum in the opposite direction. So this little rocket, I'm not going to launch it in here. It's a little water rocket, and if I launch it properly, it will shoot water down, and in the act of pushing the water downward, the water will push the little rocket upward. The problem is, it'll be like a shower in here, and you can laugh at me for the rest of the video because I'm going to be all wet. Okay? I'm not going to do that, but the idea is what I call fuel for a rocket, in this case, is primarily water. The rocket is going to throw the water down using compressed air to do that, and the act of pushing the water down and giving it downward momentum will give the spacecraft, an upward momentum, and up it'll go, despite gravity. And gravity it's present and it's important right around here, but it's not an important part of the rocket story. The rocket story is all about action and reaction. Throw the fuel out fast one way, and you get thrown the other way. The craft goes the other way. All right, so the basic idea, a basic way of looking at this is the as-launched rocket, consisting of both parts, fuel that goes one way, spacecraft that goes the other way, starts with zero momentum. It then redistributes that momentum into fuel going one way and ship going the other. The momentum remains zero in the absence of gravity, but it's distributed funny, and off goes the ship faster and faster. Now, what limits the speed with which that ship goes? The first part of the answer to that question is what fraction of the as-launched ship, as-launched rocket, is fuel? The more of that thing that you launch that is fuel, the more momentum it can carry away in one direction, and the faster the remaining spacecraft can go the other way. And that sort of makes sense, that if you're able to just keep throwing more and more stuff out the back, you'll go faster and faster in the other direction. So that's one issue. You want, at launch, rockets typically are a large fraction fuel. The more the better. Obviously, there are other constraints. You don't want it all fuel. You have nothing to. The rocket goes to space, but it's a little teeny piece that's left. Okay. Second issue is how fast can you throw that fuel out the back in the opposite direction? If I throw this baseball to the left at 100 miles an hour, well, then I get a contract with the National League. But if I throw it 100 miles an hour, it carries away a certain momentum, and I get a certain momentum in the opposite direction. But if I can throw it 200 miles an hour, I get twice the resulting momentum in me. So that's better. So the faster the rocket can throw its fuel out, the better, the more propulsion it gets out of that fuel. So you want to send that fuel out at phenomenal speeds, and in modern rockets, the ones that are aimed towards the sky and try to carry people into space above the atmosphere, around the Earth and beyond the Earth, they throw the fuel out at thousands of miles an hour. It goes out at a couple miles per second. So they use tremendous chemical potential energy in the rocket fuels. They are burning, releasing just gobs of chemical potential energy that manages to accelerate the particles that are the burning fuel out the rocket engine at miles per second. And that allows then the ship ultimately pushes that stuff very fast, very hard to get it to accelerate to that speed. And the fuel and burning gases going out, in consequence, push the rocket forward with tremendous force. and push it into the sky. So it accelerates rapidly. So you want a lot of fuel relative to everything else on the rocket, and you want to push that fuel out very fast, as fast as you possibly can. All right, that will ultimately determine how fast the remaining spacecraft goes. More fuel, faster exhaust, all good. How fast can the rocket go? Well, it turns out that it can go faster than the fuel's exhaust velocity. So that fuel can go out at 2 or 3 or 4 miles per second. The rocket isn't limited to traveling 2 or 3 or 4 miles per second. It can go faster than that. That comes about by continuing to throw fuel out, and the rocket gets smaller and less mass as this happens. It keeps on doing it. That keeps it accelerating forward. And by the time it's thrown out, for example, 90% of its launch mass as fuel at 2 or 3 or 4 miles per second, the spacecraft will have reached 2 or 3 or 4 or 5 or 6 miles per second in the opposite direction. And if they just keep throwing out more, they're down to 10% of their original mass. They just keep throwing more out, and they go down to 5% of their original mass, and 2%, 1%, and so on down. They can keep going faster and faster. And there's, in principle, no limit to how fast the rocket can go, but there won't be very much of it left by the time they've gotten to that very high speed. They will have had to throw everything else out at very high speed. Well, this notion of throwing it out and going faster and faster, you could easily figure out the total speed with which the rocket is moving by figuring out how much final mass it has, and therefore if you multiply its final velocity by its mass, you'll know how much momentum it's carrying, one way. You'd think that if you have all the fuel that was ultimately thrown out and multiply it by the exhaust speed, how fast the fuel is thrown out, if you just do that multiplication, that should tell you how much momentum the fuel is carrying away to the left, and the rocket should have the same momentum to the right. I haven't said this as clearly as I would like, but it seems like you could just write fuel mass times exhaust velocity, how fast the fuel is thrown out of the engine. That would be the momentum to the left, and you should have the same momentum to the right in the remaining craft. And that arrangement is a decent approximation for how fast, for the momentums that they're carried away, and therefore how fast the spacecraft is going. Just divide that momentum by the mass of the spacecraft and you should have its velocity. The problem is this, that the throwing out of fuel occurs while the rocket is picking up speed. So when the rocket first throws out a blob of fuel at high speed, it's motionless. That first blob comes out of a motionless rocket. But the second blob of fuel comes out of a moving rocket, one that's heading opposite the direction in which the fuel is thrown. So the fuel doesn't actually travel as fast as viewed by people who are watching the rocket launch as the first blob travels. The first blob comes out of a rocket at rest and travels at the full exhaust speed. The second blob comes out from a rocket that's moving and therefore travels at less than the exhaust speed as viewed by the people who are watching the launch. And that gets worse and worse. And as the rocket goes faster and faster and still continuing to throw its fuel out, the fuel is traveling less and less fast as viewed by people on the ground, until actually, even though it's being thrown, say, down towards the Earth as the rocket is heading up, if the rocket is heading up fast enough, the act of throwing the fuel down leaves it actually still traveling up. It's going slower than the rocket, but the rocket's going so fast up that the fuel thrown downward doesn't manage to actually reach motionlessness or even head down. It's still heading up, just not very fast. Okay, that effect, the effect that you're throwing fuel out of a rocket that is itself beginning to move faster and faster, reduces the effectiveness of the rocket propulsion effect, so that making it harder to reach really spectacular speeds. You need more fuel relative to spacecraft as a result of this effect. And so rockets, they start to struggle to go many times faster than their exhaust speed. Getting up to the speed of their own exhaust is relatively straightforward on the scheme of things. Going twice as fast as the exhaust is much harder. 3 times as fast, ooh, seriously harder, and so on. As a result of this, rockets that really want to go extremely fast, and we'll see in a minute that that's important, they need to start with an awful lot of their as-launched mass being in fuel. Huge fraction. The vast majority of the original rocket is fuel and will go out the tail at phenomenal speed. Bottling up that much fuel in a rocket that has very little mass. If you want a spacecraft to have 1 part of the mass of the rocket, 1%, and 99% fuel, that's difficult to construct. You need a bottle, basically, that almost is massless, holding all that fuel. And it turns out to be essentially not doable. People have tried. They continue to try, but it's just hard. And so they use another approach. They make staging rockets. They use more than one rocket, in effect. It's like you have a big rocket that that's maybe 80% fuel, and you launch that. And when all the fuel has been thrown out and the rocket's going as fast as it ever will go, they throw away the whole rocket shell except for a second rocket on top. So it's a big rocket with a little rocket on top. And the big rocket's job is to get the little rocket moving really fast. And once the first big rocket has run out of fuel, they throw it away and launch the second rocket. And that second rocket starts already moving very fast because it was pushed there by the first rocket. So they launch the second rocket, which is, say, 80% fuel also. They get it going really fast, and when it runs out of fuel, they launch a third rocket that was sitting on top of it. So it's a stack of rockets. It's kind of like the cat in the hat who has other cats under his hat. So this idea of staging, where you have a big first stage, a smaller second stage, a smaller still third stage, and potentially on up, has been used since the 60s at least. And it's still present in all the orbit-bound or beyond rockets. It just takes more subtle form. So, for example, it might not be one rocket stacked literally on top of the other. It may be that you launch one rocket with extra rockets clinging to its outer surface, and you use those up and throw them away, and then the middle core continues on, whether it's part of the rocket or not important. And when it's done, then you have another smaller rocket that comes off of it. And so they're all effectively staged in order to get into space. And we'll see there's more subtlety to the notion of getting into space there. So that's my story of rockets themselves. They propel themselves by throwing fuel as fast and furiously as possible in one direction and having the fuel push them forward in the other direction. I should point out that what that fuel does after it leaves the rocket doesn't matter. If it hits something, it hits a launch pad, it hits air, any of that stuff, who cares? That's the fuel's business. That's not what propels the rocket forward. It's the act of throwing the fuel out at high speed that propels the rocket forward. And so there is a lingering notion, it's been around forever, that in order for a rocket to work, its exhaust has to hit something. At the very least, the air, ideally it would hit a launch pad, something. In reality, that's a myth. The fuel, that exhaust plume doesn't have to hit anything. It's the very existence of that there's a plume of exhaust traveling like crazy in one direction. That provides the propulsion. What it hits doesn't matter. Okay? With that, then, I'm going to leave rocket propulsion and look at what happens when you actually start sending a rocket up towards space. Well, just to send a rocket straight up, suppose we did that, it would go, now, in addition to the force that I've described for rocket propulsion, namely the propulsive force of throwing fuel up backwards, there's also gravity. So a rocket that's trying to rise high in the sky and go faster and faster on a straight up path is going to have to deal with the fact that the Earth is pulling down on it with gravity all the time, and that will diminish its ability to accelerate upward, reach great speed, and so on. Okay, rocket people have to live with that. The Earth is pulling down on stuff. It has weight. This is a problem. On the other hand, they do have an advantage as they get higher and higher, but you have to get much higher, and that is an observation about gravity itself. And that is that here near the surface of the Earth, we make the approximation that gravity is uniform everywhere. That the gravity here is the same as the gravity here, is the same as the gravity down here, and so on. And that's pretty true within this room, or even within this city, or even if I go into the mountains and so on. It's pretty uniform. Not perfectly uniform, but pretty uniform. Once the rocket starts going up, 100 miles, 200 miles, or kilometers you want, just higher and higher, it's getting farther from the center of the Earth by a significant distance. And it turns out that gravity isn't uniform in that extreme case where you're really moving long distances relative to the distance to the center of the Earth. The actual strength of gravity is proportional to 1 over the square of the distance from the center of the Earth. In doing this, I'm describing the Earth's gravity. If we're dealing with the moon or the sun, we have to use the sun's distances and so on. But here on the Earth, if my distance from the center of the Earth is something like 4,000 miles, I think, about 6,000 or 7,000 kilometers. If you go up by that same amount of distance, so instead of being 4,000 miles from the center of the Earth, you go up an additional 4,000 miles, which takes you quite far up there. So you're twice as far away from the center of the Earth. The strength of gravity will have decreased by a factor of 4. So the strength of gravity is decreasing. It's going as 1 over the square of the distance between you and the center of the Earth. And that's called an inverse square law, and they're common in physics, in nature, I should say, in our universe. And so the actual law of gravity, instead of being just a constant, first off, it depends on a constant of nature known as the gravitational constant, written as capital G. It also depends on the mass of the object providing the gravity and the mass of the object experiencing it. So this will give us the force that's applied to the object. So in this case, it will be the mass of the Earth and the mass of the spacecraft, for example. And finally, it's proportional to 1 over the square of their separation. So that's the law of universal gravitation. It's the Newtonian formula for gravity, and it's good enough. In the world, finally, of modern physics, relativistic modern physics, the physics that developed during the time, for example, of Albert Einstein, it turns out the law of universal gravitation isn't quite the whole story. There's yet another level of complexity for which the law of universal gravitation is a wonderful approximation in most situations. If you get into crazy extreme situations like black holes and so on, the law of universal gravitation is not so good. But for everything, ordinary life, it's just pretty much spot on, okay? So, in this particular context, launching a rocket straight up, they have one thing that's good for them, one thing that's bad for them. The thing that's bad for them is gravity's pulling down, makes it harder for them to make progress up. So that's the bad news. The good news is gravity's getting a little bit weaker as they get higher and farther away from the center of the Earth. So it's worth knowing that that's happening. All right. That said, suppose they launch straight up. It is possible with a rocket that is potent enough, that has enough fuel compared to the spacecraft's final mass and so on. It's possible for them to go straight up and drift off into deep space. And that does come about because gravity does get weaker and weaker as you get farther away. And it is possible to actually get going fast enough and high enough that finally gravity weakens faster than you slow down because of it, and you can coast off to infinity. It is possible. It's one of these things in math. You have to do the math to get that right, but it is possible to leave the Earth altogether. But takes a mighty whomping rocket to do that. Most times, they don't get that far. So what happens? You go straight up, rocket's working hard as it can, throwing fuel down, you go higher and faster, then you run out of fuel. And gravity's still there pulling you backward, and you coast upward for a while, but you're slowing down, and you come momentarily to a stop, and then you start to descend faster and faster and faster and faster. In the real version of falling, which does take into account the fact that gravity is actually getting a little stronger as you descend. Getting a little stronger, you're accelerating downward, and plop, you land back on the Earth. Hopefully in some graceful fashion that's as you know, you don't really like to fall. It's not the falling that's the problem, it's the hitting at the bottom that's the problem. Okay, so launching a rocket straight up will take you pretty far. It can take you out of the Earth's atmosphere so that you are technically in space, and you're up there for a couple minutes. And then you come back down through the atmosphere and you land. That's okay. You can put that on your resume, been to space, okay? But if you want to stay in space, this is not a good strategy. What's the other possibility? Well, instead of launching straight up, launch up and at an angle, and worry less about getting to high altitude, apart from getting out of the Earth's atmosphere, which is 100 kilometers or so will do it. Worry less about getting altitude and more about going fast sideways. Why is that? Because once your rocket engine runs out of fuel and you now are going to be just traveling, you're going to be moving according to the forces on you and your own momentum and inertia. Gravity's going to be pulling down on you. You are not going to get away from the Earth's gravity. You're by no means far enough away from the Earth to experience no weight. No, you got a lot of weight. It's almost your on the ground weight. So if you want to stay in space, despite having a weight, you need to take advantage of, you could call it a trick, but it's right there in the physics. If you go sideways fast enough, and the air's out of the picture because you're above the atmosphere. If you're going sideways fast enough, you will be a falling object, and like all falling objects, you're experiencing only your weight, and you will be accelerating toward the center of the Earth. But because you're going sideways, that downward force on you, your weight, will not, you don't abruptly turn and head down. Forces cause accelerations. Your velocity, which is toward the side, horizontally, and very large, we're talking 17,000 miles per hour, or 25,000 kilometers per hour. It's really fast. Your velocity changes. You're curving. You're accelerating towards the center of a circle, but you're heading sideways very fast. So you're curving. Your path curves. And just as when you're on a carousel, accelerating toward the center of the carousel, that doesn't mean you head toward the center of the carousel. You bend toward it, and you can travel in a circle. If things are right, you can travel in a circle like this. And that's what happens when you go sideways at just the right speed. Instead of descending to the Earth's surface, you travel in a big circle around the Earth, which itself, of course, is a big ball. Ways to look at that idea. If the Earth were flat and you're accelerating downward, it doesn't matter how fast you're going sideways, you are eventually going to descend and hit the surface because your path is going to bend downward, and eventually you'll make progress to the surface and hit. But the Earth isn't flat, it's curved. And so as you head sideways and the downward acceleration caused by your weight bends your path, as your path bends, so does the Earth's surface. It's bending away from you because you're going sideways and you're going sort of beyond the current horizon, and the Earth is arcing downward. So yes, you bend downward, but so does the Earth. It's possible for you to make no progress toward the surface. They're both bending together. And you have to choose the right speed, but you can do that forever. You can go all the way around the Earth and never make any progress toward its surface. It bends away at just the right pace. Another way to look at this is if you go really fast sideways around this curved Earth, you'll just go straight. Your momentum will just dominate, and you'll go, inertia, you'll just go straight, and the Earth will curve out from under you, and you will drift to higher and higher altitude as you go in a straight line. You will just leave the Earth behind and go to ever higher altitude. In fact, there'll come a point where calling it altitude doesn't even make any sense. The Earth is a light year behind, who cares? So, at very high speeds, you go to higher altitudes, and then off into the stars. If you go too slowly, at very low speeds, gravity wins. The downward acceleration becomes strong enough, you make so little progress sideways, that you descend closer and closer to the Earth. In fact, that it's curving away doesn't even matter, you just plop. Okay? So at low speeds, gravity wins, and you go to lower and lower altitudes. So go in between. Super fast and you go straight to higher altitudes. Super slow, you go curve to lower altitudes. Split the middle and go to constant altitude. And so it is possible, if you go sideways at the right speed, to stay at constant altitude around the Earth. And that, of course, is an orbit. In this case, specifically, it's a circular orbit, because you're traveling in a circle around the Earth. And to obtain a circular orbit, given a certain altitude above the Earth's surface, or alternatively a certain distance from the center of the Earth, you have to go at a specific speed to maintain constant altitude and to travel in a circle. If you go a little too fast, you will, inertia will win a bit. You'll go a little to higher altitude. As you do, you will slow down because you will have been converting some of your kinetic energy into gravitational potential energy. So eventually you'll stop going to higher altitude, assuming you don't go too fast. You didn't start too fast. You'll go to somewhat higher altitude, and you'll swoop back down to lower altitude, and you'll travel in an elliptical orbit. So elliptical orbits occur when can I go around? Here's an elliptical orbit. You start at low altitude, but you're going too fast. You arc out to higher altitude, and then you swoop down to lower altitude. To higher altitude, and then just lower altitude. And you're going slower out here than here. So it really do this right, it's in fast and then out. And then fast and then out. So that's an elliptical orbit. If you're in here and you go, of course, if you go too slowly, you go to an elliptical orbit that brings you down to the ground, which is maybe fine for landing if you plan on that. Circular orbit, you're going just the right speed to circle at constant altitude. A little faster, you go into an elliptical orbit, and if you go especially fast, the bending process will lose and you'll go off into deep space. And these orbits are parabolic is one and hyperbolic is the other. It depends on how fast you go from parabolic to hyperbolic. They do go off forever. And the orbits are part of all of our space fun and games that we've done since the 50s and 60s. We put stuff in orbit routinely now, and most of them are circular orbits or very nearly circular elliptical orbits. They're obtained by taking a rocket, launching a rocket, having it not concentrate on going up, but rather concentrate on going sideways to get that high speed sideways that you need in order to swoop around the Earth and make little progress toward its surface. To get away from the Earth, they speed the rocket up sideways even more so that it travels not in a circular or elliptical orbit, but actually in a parabolic or a hyperbolic one, and therefore leaves the Earth altogether and goes to some other place. If they want to have it explore the moon, they take it in a parabolic or hyperbolic orbit that brings it close to the moon, and then when they get there, they slow it down. So that instead of whipping around the moon and leaving, it gets trapped in one of these circles or ellipses around the moon, and so on. They work their way back. So it's just all a game of ellipses and circles, and they're all technically under what a mathematician would call conic sections. Shapes you can obtain by taking a cone and slicing it with a plane. Circle, you slice horizontally. Ellipse, slice at an angle, but come out the other side. You want a parabola, slice parallel to one of the far side. You want a hyperbola, slice something at a steeper angle. So they all come out of cones. Anyway, so that's the world of orbits. They're all the result of traveling sideways so fast that you don't make significant progress towards the center of the planet you're going around, you're orbiting. In fact, you travel in one of these conic sections. Okay, a couple of observations. Many years ago, centuries ago, Johannes Kepler observed 3 interesting features of planets orbiting the sun. And he didn't know the math, but he just made these observations, and they turn out to be well justified based on mathematics. And I'll tell you the 3 observations. They're called Kepler's 3 laws. They're worth knowing they exist and seeing them briefly, and then you can set them aside. His first law is that these orbital shapes, the planets are all traveling in shapes that are ellipses. Technically a circle, technically I should be careful because I'm not that kind of a mathematician, not a good enough mathematician to say for sure. A circle is just a special ellipse. It's the most boring of the ellipses. Ellipses have 2 effective centers. They have 2, I think they're called foci or loci. They're 2 special points in the middle of the ellipse around which the ellipse is constructed. And if those 2 points happen to coincide, at one point you got a circle. But for the planets going around the sun, they're all traveling in orbits that are not perfect circles. So they have 2 of these special points. And one of them is right at the center of the sun. So that was Kepler's observation, is that planets orbit in ellipses with the sun at one of the, I think they're called foci. Okay? Second observation that Kepler made was that if you look at the planets as they orbit the sun, even as they come closer and farther whipping around the sun, they sweep out the area they sweep out between the center of the sun and the planet itself, as it sweeps across. My hand as I sweep is describing a slice of pie, like pie like you eat. That the area of that surface that I'm sweeping out as a planet, it's constant in time. Every second it sweeps out the same amount of area. That means that as the planet gets closer to the sun, and the length of the string connecting the sun to the planet gets shorter, the planet moves faster to sweep out the same amount of area every second. And so he just observed this. It's there, and sure enough, that's true. And it can be mathematically justified now that we know all the laws of physics well. It falls right out as an observation that's correct. And the third thing that happened that we observed is the square of the orbital time, how long it takes a planet to go around in a loop. If you take that time and you square it, and you divide it by the cube of the average distance the planet is from the sun, you get a constant. Is that true? See how well I remember Kepler's third law? I'm not confident about it. The point is that he found a simple law that tells you how long it takes a planet to orbit the sun based on its mean distance from the sun. So the planets that are in close, their orbital time, Mercury for example, has an orbital time that is determined by the fact that its mean distance is close, and he came up with a formula for that. On the other hand, a planet like Jupiter, much farther away, it's got a much larger mean distance, its orbital period is much longer. It takes much longer to run the sun, and he found a formula that fit it. And again, it's a formula that comes right out of the mathematics of doing basic laws of motion, Newtonian laws of motion, and the law of universal gravitation. There it is. So those are Kepler's laws. I'll obviously test you on Kepler's third law, since I can't remember exactly the form anyway. Last thing to mention here, and that is, and I will sort of mention these briefly, and that is these laws of motion that I've been describing up to this point in the semester. Newton's second law, for example, that an object accelerates when exposed to force, and if you take the force exerted on it and divide it by its mass, you get the acceleration. That's one of Newton's laws, and it's very accurate, but it's not perfect. it turns out that Newton's laws of motion, all of them, for rotation, for translation, they're not quite perfect. They're approximations of a better law. There's a better law that describes the laws of motion. There are a better set of laws of motion for which the Newtonian laws are an excellent approximation at ordinary speeds, and a few other criteria in this situation. But when stuff starts going really fast, like if you start going to the stars and you want to get to those stars, stars are very far away. And if you want to get to those stars in your lifetime, you are going to have to travel very fast. Not just ordinary rocket ship fast. You're going to have to go fast, like getting into the territory of the speed of light, which is seriously fast. And if you start traveling that fast, the conventional laws of motion, the Newtonian ones, aren't so good anymore. And what's starting to go wrong? Well, it turns out that if you keep pushing something forward and thereby increasing its momentum, you would think that with every dose of momentum, it's going to go one dose of speed faster. As you start getting closer to the speed of light, that's not true. You keep giving it the momentum, but its speed doesn't increase as much as you would expect. And its speed gets closer and closer and closer to the speed of light, but you can't actually get there or exceed it. So objects, as they get closer and closer to the speed of light, they still have the momentum, and you keep adding more by doing impulse, but they don't, their speed doesn't increase in proportion, and therefore they start behaving, they don't behave according to Newton's simple laws. For most purposes that doesn't matter, but it does start showing up in some of the systems that we deal with. In fact, in everyday life. The satellites that are orbiting the Earth, the GPS satellites, they're knowing where they are and when they are, the time and stuff. They have to be controlled extremely precisely to know exactly where you are. And these, what are known as relativistic effects, become important. And so the GPS satellites prove every day that the laws of motion, the real laws of motion, as best we know, are relativistic ones. And if you don't take into account the relativistic aspect of the motions, they won't be able to tell you where you are as accurately as they do. And so there are other situations like that, particularly with fast-moving stuff, where you need to consider the actual relativistic laws of motion. The same with the laws of gravity. The Newtonian law of universal gravitation, that is the force of gravity between two objects, has this constant g times the mass of one, the mass of the other, divided by the square of their separation. That's very good for most circumstances. But in extreme cases, like near a black hole, it's not good at all. And you need to use the more accurate laws of gravitation, which are those included in the theory known as general relativity, another of Einstein's discovery. Einstein came up with special relativity in 1905, and general relativity, I believe, was in 1912. So they're separate but phenomenal theories. They're intertwined, but one's associated with just sheer motion, that's special, and the other's associated with gravity, that's general. Anyway, it's worth knowing those exist. Will we ever use them in this class? No, but there they are. And so that's really the story of rockets, from the act of launching the thing and getting it moving, to sending it around planets and off into space, and finally what would happen if we could actually make rockets that travel at nearly light-like speeds. Then we would have to be dealing with more sophisticated laws of motion.